everyone. My name is Hunhan, a machine learning engineer from Superb AI. Today, this talk is about how to label and manage a huge data set in the event of AI at scale. So, as you all know very well, the data set used for training a model is getting bigger and bigger in the academia and industry. So such trend is quite clear, I would say. And as you can see in this graph, that the size of the data set that's used by the academia is getting bigger and bigger. So this trend is quite clear in the industry as well. And the problem that we'd like to tackle in this talk today is what are the challenges that we have on building and managing the large data sets, and how can we address such kind of issues? So to make it simple, I just bring one persona of an MLE, whose name is Denny. And he is a machine learning engineer who is currently working on developing a CV model to detect the objects on the road. So we're going to go through the steps that he needs to make when building up the model to detect the road objects one by one, and to discover the challenges that he likely to face in the future. So first of all, because when training a model and deploying a model, he needs to set up the baseline so that he can compare the performance of the model and see if the model he is training is working well or not. So before all those steps, he probably can use the data set that is already publicly available, or data that's scrolled from the web that's usually of very little cost, right? So he can train the baseline model for that purpose. And afterwards, to train his own model, he needs to collect the data on his own. So he needs to collect, let's say, 1 million images, because this talk is about collecting the large data set, right? So he collects 1 million images from the road while driving. And this cost to collect the data increases proportionally to the size of the data set that he wants. And this step 3 sometimes needs to be done before step 2. That depends on the specific tasks that the MLE tries to solve. And anyway, the labeling guideline works as a ground truth to the labeler, so it needs to be comprehensive and accurate. If there is one controversial point, even if it is one just single tiny controversial point, but when it's found during the labeling or after the labeling, then the relevant data that's related to the controversial point needs to be relabeled over again. And this actually dramatically increases the labeling cost. So we need to be take care of the labeling guideline very much, so that it needs to be accurate very much. So we don't have to work over and again repeatedly. And the labeling guideline should include answers to the questions from simple on which objects to annotate, or to the controversial ones, like how to deal with the data object with occlusion, truncation, and blurs or something. So this kind of information can help labelers to not make an ambiguous decision when the labelers make annotation. And specifically when the data set size is huge, like 1 million images, he will need a lot of labelers to work on. And this itself requires a huge cost. So in this manner, he needs to distribute the labeling task to both in-house labelers and third-party labelers. Of course, he can afford the cost to label all the 1 million images in this step, but since most of us are under the limited time and budget, so he might need to choose which data to label to train the model. And this is one issue. And on the other hand, the cost to coordinate issues arising from the labelers is not ignorable as well. As I mentioned in the step 3, Yeah, of course, he needs to build up. He needs to write comprehensive labeling guideline with his best. But if it, yeah, he needs to prepare for the plan B. So writing a great guideline is important, but yeah, to prepare for the unexpected issue. So he needs to think of what to do next. What to do? What if when the labeling guideline is found to be ambiguous? And all set, he has all the data set with the labels. Then the next step is going to be training a fast RCNN or something like object detection model with the data set that he has. And when the training is complete, the next step is just to find the weakness from the data or model and give feedback. Give feedback to the overall workflow. And the common issues he can find from the analysis are, for example, lack of edge case instances or the existence of mislabeled instances, and so on. So when this kind of issue is discovered, he needs to make up for that and iterate this process from somewhere, again, from 3 or 4 or 5. So yeah, I would say this is the usual workflow that one MLE can go through when trying to solve a problem in computer vision. And yeah, so what we've been through so far with Danny's scenario, I simplify them into this diagram. We first need to collect the data set and label the data, and if just review the data if there is any mislabeled instances or something, if there is any issues that we need to care for, like diversity or something. And yeah, we're going to go back and forth a few times in this diagram. And after this step is done, we train and test the model. When the training a model is complete, we need to analyze the weaknesses. And then the decisions that we can make after this step is probably collecting more data that's not enough, or we can correct the mislabeled instances or errors in the data set or something. So this overall workflow can be this overall workflow can usually iterated over and again to improve the performance by the MLEs. And yeah, as we have seen in the Danny scenario, in each step of the workflow, there are challenges that MLEs usually face, especially when we're trying to build up the huge data set. So for example, when collecting the data, the cost to data collection increases along with the data size. And of course, and also ensuring the quality of the data, such as diversity and correctness, is getting difficult as well as the data. The data set size is increasing. And when it comes to labeling and reviewing, if we rely on human only, then the cost, not just the monetary, but the time cost as well, it would definitely be huge. And what if the task requires the domain knowledge? This is also another problem that we need to think of. And when the labeling task requires the domain knowledge, then the cost to recruiting and training the labelers becomes much, much more expensive because the task itself is very difficult for them. And even when we try to analyze the weakness out of the huge data set, simply a list of data would make it difficult for us to find an object or understand the data landscape and so on. So it is not an easy task at all to build and manage a dataset as an MLE, but the cost increases dramatically when we need a large size dataset, especially. All right, and in the following slides, I will introduce the features of Superb AI that are designed to reduce the cost on client side when building up such a large dataset. First, let's say you have your own in-house data labeled. Let's start from that, but need some help managing the data. So then you might want to find the data based on the metadata like name or number of annotations. And over the course of iterations, you will likely keep updating the data over and again. So in this case, the data versioning would help you manage the history of data that you've improved. And the other parts that we're going to go through in the later slides. So for example, the advanced query is help you find the data based on metadata like name or annotations. As you can see, the metadata, the annotation of number of counts in the number of card objects in an image. So when finding a data instance, you can use information like just simple metadata or annotation information in this kind of search engine. And further, yeah, because it's going to be, it can be quite difficult for the MLEs to write up the query to find the data instance that they are looking for. So this query builder helps users to make a query based on the metadata that's accessible by the system. And also it supports the types of operators like and or between a unique query. So yeah, a user can easily see how the query looks like and find where to fix when necessary. All right. And from now on, let's say you don't have your own data, so you need to start from the data collection. And yeah, it's going to expose you to more diverse, difficult problems while collecting the data. So this diagram shows how the technologies can improve the efficiency of the data ops workflow. We'll take a look at each feature one by one, but overall, after collecting the data, yeah, of course, some like 10% of the data should be labeled manually, and this portion of data can be used to train the model to label the rest of the data. So after the manual labeling, we can apply the auto label. We can train the auto label model and apply the model to label the rest portion of the data. And yeah, as you can see in this green section, when all the data set is labeled complete, then we need to review the data to see if the data is reviewed. To ensure the data quality, like accuracy and diversity. So for these cases, mislabeled detection or uncertainty estimation can be applied to ensure the quality. And afterwards, the creation technology is to recommend the users the task set of the widest coverage so that we can rely on the task performance. We can rely on the task performance after training. And when the training is complete, then we need to analyze the weaknesses using the semantic search engine and the data curation technology once again. So as I mentioned in the slides earlier, after this step, we need to make a decision whether to collect more data or correct errors. So yeah, let's go each feature one by one, and how can we reduce the burden when building up the huge data set. All right, so when it comes to an image data set, it's really boring and erroneous job for human to draw every boundary of an object. So this labeling task can be much easier and more efficient with the interactive labeling technology. So the interactive labeling, with the interactive labeling technology, it needs, all the labeler needs to do is click where to include or not. So for example, instead of drawing every boundary of this cat, one just needs to click to indicate where to include, like green dot, and where to exclude, like red dot. So this actually reduces the burden that the labelers have while while labeling objects in the dataset. This is just another example that we apply the interactive labeling technology to another data. So green dots include where to include. And because this is quite inaccurate, so add the red dot to indicate the regions to exclude. Yeah, so this way we can reduce the burden of the manual labeling. Of course, it is going to be better for us to rely entirely on the machine to label the whole data set, but it is not possible. We need to provide the machine the ground truth data. And so at least for like 10% or 5% of the data the manual labeling is required. And this kind of technology can reduce the burden for such instances. Yeah, and after this, we have a manual. We have a data that is labeled manually, and yeah, at last we can defer the labeling task to the machine. So yeah, this can dramatically reduce the cost for us to label the data set. Yeah, when we have we have two different types of auto label, and one is the predefined model, pre-trained model that can directly be applied to label the data set for 100 and more common objects. So let's say we are supposed to label a fruit in the data set, then you can map your label fruit to banana, apple, and orange. So this kind of predefined features. Yeah, and now the auto label AI is created, and we can just apply that AI model to the raw data. Or if you need more detailed and accurate labeling with this feature, because, for example, the class set of your data set is not common, or your data set mainly includes the edge cases, so you think it might not work well with the predefined model. So you can also feed your own ground truth data to train the auto label model. So you can specify the data set that you would like to use to train the auto label model here. And when it's done, then auto label AI model is created. And after this step is done, so this below, the agriculture cal is the auto label model that is already trained. So once the training is complete, we can just apply this model to label the rest of the data set. So this is how auto label works. And yeah, as you can see, this can reduce the cost to labeling the whole data set very much. But however, there's no 100% perfect machine. So in this auto label feature, we also calculate the uncertainty of our auto label model and provide to the clients. So based on the uncertainty value, the clients can set the priority to determine which data to review first. So the first image we are looking at is indicated as difficult. And if we look at this image, there are many fruits in the image, and some of the fruits are hidden behind the leaves. So it seems this image needs quite a human touch. But for the image indicated as confident with the green dots, if you take a look, there are fewer fruits in the image, and few fruits are hidden behind the leaves. So as such, the image with high uncertainty is recommended to review first by a human. And based on our client's experience, the labeling time with our auto label is found out to be reduced by 10 times compared to manual labeling overall. For example, with our experiment with the person images in the COCO dataset, only 1/3 of the hard examples are needed for labeling. So, which means that a huge reduction in the manual labeling cost. So with this kind of auto labeling technology, you can expect a reduction of cost to label the huge data set and not relying much on the human labelers. And the next thing that we're going to go through, we're going to take a look is mislabel detection technology that actually helps clients review the data set. So still a majority of Diffusion data set is labeled by human. And this mislabel detection feature tries to reduce the errors from such data sets. So when a client puts so-called reference data, which works as a ground truth to this mislabel detection feature, our detection engine runs to find the likely mislabeled data. So all you need to do is just prepare for the data and that has the ground truth, and feed the ground truth data to the engine, mislabel detection engine, and click the run button. And wait until complete. And once this mislabel detection is completed, you can track the detection results right away. So as an example, this demo video shows the result of mislabel detection conducted on the publicly available dataset BDD100K. If you take a look for the car class, there seems to have quite a few incorrectly labeled bounding boxes. For the traffic sign, there are some blurred objects, and it seems like a park sign over here. For the traffic light, there are a few incorrect bounding boxes as well. Yeah, as you can see. And let's take a deeper look at the result of the traffic sign class. So you can open up the original image and zoom in to see if it's really mislabeled. So if you find that it's really a mislabeled instances, then you can leave an issue right away so that labelers or data project manager can reflect those issues referring to your comments. Yep, so all set. And this is how the mislabel detection goes on our suite platform. And the next thing that we're gonna look at is embedding store that makes it available for us to run semantic search and data curation. We wanted to support not just various features that are helpful for managing the dataset, labeling the dataset, and reviewing the dataset, but we also want to support the the features that help managing the dataset, like semantic search and data curation. So we come up with so-called the embedding store that can support such features with embeddings, either that clients make on their own or that we extract using our own model. So embedding store enables the clients to support the semantic search. You can just think of it as a search engine like Google does customize the client's dataset. And this search engine, because this is run based on the embeddings, is semantic embeddings, so we can take both natural language text and image as query. Like this, the query can be yellow car and bus, or you can just load from image from local and proper region to indicate an object of interest. And once the search is completed, you can find the search engine result right away. And it seems the search result includes car from the dataset, and there is a yellow school bus over there as we give a query to the engine. So then if you think you find the appropriate results that's fit for your needs, then you can put the tag on them for the later use or share it with someone else. And another feature that embedding store supports is data curation. So instead of getting a validation stat or test set for random split that we usually do, it helps you get the test set that has the widest coverage. So it may include more diverse cases and edge cases. So in this way, you can rely on the test performance, and you can say that test performance is more robust. After the data curation, we provide users with a report like this so they can easily check how our created data set is better compared to the random split one. It includes the general information like class distribution at the top, like class distribution over here. Looking at the cluster coverage over here. And you can find that our created data set has better coverage in terms of clusters. This likely leads to a semantically diverse data set. And you can also find where images are more selected in the created data set. And with this 2D visualization, it's easy to find that created data set has wider coverage than random one. And also, this sample images help clients get the overview of what the clusters look like and what kind of images that clusters have. And they can see that each cluster truly has diverse images compared to the randomly selected cluster. Oh, yeah. So that's it for us today. And thank you for watching.